Hello everyone, wherever you may be. I hope you enjoy the coming presentation. The objectives of this research were as follows. First, to describe a methodology designed to carry out an assessment of the effect of vegetation on annual building energy consumption, accounting for effects of urban microclimate. And secondly, to illustrate it by means of a case study for several residential building types in a warm climate. The case study focuses on a dense, medium-rise neighborhood in the city of Tel Aviv, which has a Mediterranean climate with mild winters and hot, dry summers. The study was carried out using computer simulation in two distinct and separate stages. In the first stage, urbanized weather files were generated from reference data measured at a rural weather station for three different scenarios: an existing street canyon and the same canyon with more vegetation or with all existing vegetation removed. In the second stage, building energy consumption was simulated in 5 scenarios: a standalone building at the rural reference station, the same building but shaded by adjacent structures, conditions in typical streets in Tel Aviv incorporating urban factors such as anthropogenic heat and shading, and 2 scenarios similar to scenario 3 with additional plant cover up to 50% of the non-built area or with all existing vegetation removed. Urban microclimate was simulated with a model that I call CAT, for canyon air temperature, which was developed about 15 years ago. As the figure shows, the correspondence between the predicted air temperature at Tel Aviv beach, indicated by the solid red line, and the measured data for the same location, indicated by the blue circles, is quite good, despite the fact that there is a substantial difference between these data and the temperature record that was used as a reference, indicated by the solid green line. For details of this particular model, please refer to papers listed at the bottom right-hand side. The air temperature simulated for the urban street canyon is nearly always warmer than the temperature measured at the rural reference site. However, this difference is not constant. It has a typical diurnal pattern. The intensity of the urban heat island is greatest at night and is minimal during the middle of the day during the hot hours. Even at night, there is a large variance. Some nights have a minimal urban heat island of less than 2 degrees. Other nights, this difference is almost 6 degrees. The effect on air temperature of adding vegetation was also modeled with the canyon air temperature model. What you see here is a summary of the results using ensemble data for an entire year at hourly resolution. The temperature reduction that is affected through the addition of vegetation is typically modest, rarely more than several tenths of 1 degree, and always lower than about half of 1 degree centigrade. This is because the amount of vegetation that you can realistically add is limited by the current situation in the street. You can add, say, up to 50% of cover for the ground surface area, and this is what we have modeled here. Building energy performance was first simulated for a standalone building. The building has 4 apartments per floor and a total of 8 floors. It was then simulated with the addition of adjacent similar buildings surrounding it to generate shade representative of what a building would be exposed to in a city. The building itself is a standard Israeli building, a fairly low level in terms of thermal performance, 20 centimeter hollow concrete blocks on the walls, flat concrete roof, and single-glazed aluminum windows. The heating, ventilation, air conditioning set points were 20 degrees centigrade in winter, 24 degrees in summer, and the occupancy schedule and internal gains were fixed according to Erell Standard 5282. The output of the building energy simulations is summarized in the following graph. As you can see, shading by adjacent buildings increases heating but reduces cooling demand. Moving from a rural area to the city reduces heating and increases cooling demand due to the urban heat island. Adding vegetation reduces cooling demand, and removing existing vegetation increases it. The annual energy demand depends on the balance between heating and cooling, which is specific to each location and climate. To summarize, actual percent energy saving from vegetation will vary from place to place, but it is likely to be in the low single digits. To estimate energy saving, we need detailed building energy simulation software that is capable of performing dynamic calculations for an entire year, not just a hot day in summer. Urban effects must be accounted for in the weather files used as input for building energy simulation. The magnitude of these effects is often greater than the impact of the mitigation measures proposed. It is essential to model the effect of shading by adjacent buildings or any other sizable object, including trees. And finally, let us remember that energy savings also depend on occupant behavior. That's us. Those of you interested in more information about the canyon air temperature model are encouraged to refer to the references listed here for your benefit. They also appear, of course, in the printed version of the paper. Thank you for your attention.